Welcome, everybody, on this beautiful October afternoon. This afternoon, our Jones speaker is Professor Don Perovich, and he's going to take us all to the Arctic Ocean. Things are changing rapidly there, and this will be an exciting talk. Don received his PhD in geophysics from UW, and after working at Krell for a number of years, he has come to the Thayer School of Engineering, where he is mentoring students who are also working in polar science. Don has an impressive array of scientific leadership behind him, of course, always in person in the field. He was chief scientist a number of years ago on the Sheba expedition, the surface heat and energy balance of the Arctic Ocean, a very successful expedition. And he's also currently one of the co-leads on IceScape, the impact of climate change on ecosystems and chemistry in the Arctic Pacific environment. Most exciting, he's co-leader of the snow and ice team for MOSAIC, what we'll hear about today. Don has an impressive list of publications, basically in global science. If you talk about sea ice, people think Don Perovich. He's been PI on multiple research grants from the leading research agencies, NASA, NOAA, NSF, the Navy, Office of Naval Research. And he has a patent on a buoy for automatic sensing in the Arctic Ocean. Over time, he has accumulated a number of very impressive awards. I won't go through the whole list, but they include awards from NASA, from Krell, and the U.S. Coast Guard, and elsewhere. He's a fellow of the American Geophysical Union, and today we'll hear about the dramatic changes that are happening in the Arctic Ocean from an expedition, a ship frozen into the sea and drifting across the high Arctic. Come to the Arctic with Don Perovich.
Thanks, Mary. The Arctic Ocean is a harsh environment. There's months of unrelenting darkness, high winds, blowing snow, shifting ice that can break apart underneath you in only minutes. It's really a harsh environment. Trust me, I've been there. Paradoxically, it's also a fragile environment. The Arctic sea ice cover is fragile because it's a material that's near its melting point. And that makes all the difference. So let's take a quick look at the Arctic sea ice cover. It's the frozen ocean at the top of the world. The sea ice cover is vast in areal extent, covering millions of square kilometers, but it's just a thin veneer of ice, only a few meters thick. It's young ice, anywhere between a few months to a few years old. And always remember, it's a frozen ocean, so it's floating, and it moves. It moves kilometers to tens of kilometers per day, driven by winds and currents. And as you can see, it's bright and it's white. It does a good job of reflecting sunlight. And the reason we've become interested, even more interested in the sea ice cover in recent years is because of its role as an indicator and an amplifier of climate change. Well, how does that work? Well, we can use Arctic sea ice as a proxy for temperature. Think about it. We have this ice cover that's vast in areal extent, but thin, and it's also near its melting point. So we would expect if there was warming, we would get less ice, and if there was cooling, we would get more. And indeed, that's what we see every year. The ice extent expands in winter, reaching a maximum in March, and declines in summer, reaching a minimum in September. But we're not interested in looking at the seasonal cycle. We want to see if there's any signal from climate change. And to do that, we focus on 1 month, September, the end of summer, where changes are the most evident. And what you see here is a simple plot showing the ice extent, millions of square kilometers, at its minimum in September from 1979 up until a few weeks ago. And if you look at this, you can see that there's very large interannual variability. In the beginning of the record, we have times where we have the lowest we've ever seen, followed by the most we've ever seen. But if you look beyond that variability, you'll see a distinct downward trend. And we can do a simple linear fit to this trend and see that there's a decrease of roughly 13% per decade. Now, that may not seem like much, but it adds up over 4 decades. Now, this does a good job of showing us numerically how the ice is being reduced, but it doesn't say anything about where it's being reduced. And we can take a look at that by picking out 2 times. We can pick out 1980, also known as the good old days. Off the coast of Alaska and off the coast of Russia, reducing the ice extent to 3.4 million square kilometers, a total loss of 4.4 million square kilometers. Well, the problem is with numbers that big, it's often hard to determine what that really is, to get a sense of what a loss of 4 million square kilometers is. But fortunately, it just so happened that back in 1980, that 7.8 million square kilometers was around the same size as the continental United States. So we can ask ourselves, how much of the United States melted? A lot of it. It's as though the entire US east of the Mississippi completely melted, plus the band of states from Minnesota all the way down to Louisiana, plus North Dakota, South Dakota, Kansas, Nebraska, and Oklahoma. This is a huge loss of ice. The loss of ice the Arctic has experienced over the past 4 decades is significant. Now, if you look at this time series, it's become the iconic sea ice climate change signal. And it's been studied by everyone. We've looked at it to the point where you start seeing all kinds of things in the data. Different curves have been fit to it. Frequency analysis, it's been related to different atmospheric parameters like the North Atlantic Oscillation. But we can look at this and we can see something really interesting, and that happened in 2007. In 2007, we set the record minimum ice extent up until that point, and it was done with the largest year-to-year drop we ever saw. And there's never been a larger drop than that year. And so if we look after 2007, we see that there are years where it goes up, and there are years where it goes down. In fact, the behavior after 2007 looks fairly similar to the behavior in the good old days, but it's never gone back to the levels before 2007. It's as though the ice state dropped into a new normal of less ice extent, thinner ice, younger ice. It's the new Arctic Ocean. And as sea ice people, or actually Arctic Ocean people, we talked about this and we realized that we needed to learn a lot about this new Arctic. We had plenty of measurements on the old Arctic with more ice and thicker ice, but there was so much we didn't know about this new Arctic Ocean. And that provided the motivation for MOSAIC, the Multidisciplinary Drifting Observatory for the study of Arctic climate. The centerpiece of MOSAIC was the year-long drift of the icebreaker polar stern. The idea was freeze an icebreaker into the ice and just drift with the ice pack for a year. And that's what was done. From September 2019 to October 2020, the polar stern executed the drift. So MOSAIC was governed by an overarching science question: whether the causes and consequences of an evolving and diminished Arctic sea ice cover. That was the broad question we were trying to address. Underneath that question, there are 5 subsidiary questions. What affects the heat momentum budget of the ice? How does first-year ice move into form, this younger ice that was covering an increasing amount of the Arctic? What processes contribute to clouds and precipitation? And what are the cycles of ecosystems and biogeochemistry? And then looking at all these changes that are occurring in the Arctic Ocean, how does that impact the rest of the Arctic system? We wanted to go out and observe and understand the new Arctic Ocean, this Arctic Ocean with less ice and younger ice. There's a lot of things about MOSAIC that we'll hear were unique, but for me, one of the biggest changes, one of the biggest improvements from the first day of planning back in 2009, it was observers and modelers working together. It wasn't the usual thing where observers designed an experiment. We sat down with the modeling community and say, what are the limitations of climate models? What are processes that are poorly understood and need improved parameterizations? And so the modeling community went through, they ran simulations, they looked at single column models and said, these are areas that we need to improve. And to get the data we need, here's a recommendation for the kind of measurements to make. We made those measurements, now we're analyzing the data. It's going back into developing parameterizations for the models, and we're completing the cycle. We have a virtuous cycle of models first informing observations, and then using those observations to improve models. So let's take a look at MOSAIC by the numbers. MOSAIC was the biggest Arctic Ocean experiment ever done. It was highly interdisciplinary and international. There's a general principle for Arctic research: the bigger experiment, the longer it takes to plan. And the MOSAIC planning lasted a decade. It was highly international with 19 different nations contributing. It took 5 ships contributing in one way or another. It was pretty expensive, somewhere north of $150 million. But again, there were 19 countries, so it was a very collaborative effort. There are 600 experts involved in it, and there are 5 legs. In this year-long drift, it's important to remember that nobody stayed the whole time. Some people stayed large portions of the whole time, but there are rotations where crews could be exchanged and supplies could be built up. During the course of the experiment, it went over 390 days. Of those 390 days, 120 of them were total darkness, and the ship drifted around 2,500 kilometers. It was a very big experiment. Now, all those experts and researchers were organized into 5 teams, looking at the atmosphere, sea ice, the ocean, biogeochemistry, and ecosystems. And each team had their own responsibility for various measurements, but they weren't working in isolation. There was a realization that this was a system and that we all had to be working together, coordinating things. Just for an example, as an ice person, I'm interested in how sunlight interacts with the ice cover, because that affects how the ice melts. The atmosphere group wanted to know as well, because that affects the surface energy balance. The ecosystem people wanted to know how much light got through, because it impacts primary productivity. And there were numerous contributions like that where things really need to come together. And tying it all together was modeling. The modeling was touching all these different elements of MOSAIC. Now, another important component of MOSAIC was outreach activities. This was a huge experiment, and this was a tremendously exciting experiment. And we wanted to share it with everybody. There were public lectures. Members of the MOSAIC team have done a lot of lecturing over the past few years. There's also a Coursera module on MOSAIC, which you can find online. There are also numerous interactions with the media, some of which are still ongoing. And there was a book. A book's already come out, Into the Arctic Ice, that has beautiful pictures from MOSAIC. Outreach was deemed to be so important on MOSAIC that throughout the whole experiment, there were always 2 people their job was to do outreach. There's also TV shows. Tune in this coming Wednesday, October 13th. NOVA's having a 1-hour episode on MOSAIC. And there's a planetarium show coming soon to a planetarium near you. And finally, we really wanted to do outreach to schools. There was a lot of K through 12 outreach. Our particular project, we brought students from Hanover to Boulder, Colorado, and at Seattle, Washington. We wanted to engage everyone in polar research. Now, we have all these measurements to make, and the question is, how are we going to do it? And where are we going to do it? And it's easy to say this is a vast ice cover that has millions of square kilometers, but we are just focused on an area, the ship, and a few kilometers around it, the central observatory where most of the observations were made. And when you have something like that, and you're going to spend a year on the ice, you really have to work hard to ensure you don't use up the area. And so when we were planning, we decided we need strict zoning laws about where you could go, setting aside areas for different kinds of research and for collaborative research, where the roads would go, where the power lines would go. And we were actually able to execute this. You can see the image on the right. That's a false color image of surface elevation taken from a LiDAR based on a helicopter. And the white areas represent pressure ridges where the ice is piled up. And it was divided up into areas, an area to measure albedo, another one to take ice cores, one to do mechanical tests on the ice. There were even recreation areas. There are ski tracks around. I don't know if they were groomed or not, but there was plenty of outdoor activities you could do. So we made this effective use of zoning laws. Now, you realize that spending a year on the ice is a difficult challenge. There are many challenges to work out, and winter in particular is tough. Again, with these high winds and blowing snow in the months of total darkness. And so even before we went into the field, we developed protocols. What we would do if it was below a certain temperature or above a certain wind speed. So we had these protocols in place to deal with some of the challenges of working in the winter. And as always, you're floating on an ocean. It's easy to forget that sometimes until a crack opens up and you can see the ocean right there. And what breaks apart can come back together, forming pressure ridges, mountains of ice. And so here too, there were written protocols about it. But what was most effective is we brought a lot of lumber and a lot of spare parts for the instruments that we knew eventually some would be crushed. And then there's visitors, visiting bears. And that was a concern. We knew that there would be a lot of bears where we are and how to deal with it. And again, there were protocols. There was page after page of how to deal with bears, how to operate on the ice. Well, what it came down to summarize, this is the bear's house and we're just visiting. And so whatever interactions there were with bears were fine. They did exhibit some curiosity about our instruments. Now, winter is definitely the toughest time with the temperatures and the darkness, but spring and summer have their own challenges. The weather is nicer, it's sunnier, there's daylight 24 hours a day, and there's also warmer temperatures. But that can create problems as well. Here you see in this picture, the ice is broken up a little bit, and that's fairly common throughout the entire year. In the winter, you would wait a few days, and those open areas would freeze over. Doesn't happen, though, in the summer. You have to figure out a way to work around those areas of open ocean. And then melting complicates mobility. In the winter, it's not that hard to get around on the ice. What you have is a snow cover that's wind-packed pretty hard. You can walk on it easily. You can snow machine on it very easily. But this nice wind-packed snow cover, when summer rolls around, it begins to melt, and it just becomes a slurry of snow slush that you have to wade through for a few weeks until it completely melts. And that meltwater, some of it accumulates on the surface, forming these nice blue areas called melt ponds. And they too provide a challenge. But again, we had plenty of lumber and some very nice bridges were made. But in general, melting complicates mobility. Also, melting can make some measurements difficult. Here measurements are being made in the melt pond, and these ponds were of particular interest because of the impact they have on the solar radiation budget. They're darker than the surroundings, they absorb more sunlight. Also because they store meltwater, which has an impact on the thermohaline structure of the upper ocean. And the ECO team was interested in whether or not there was any sort of biological activity in these ponds. But MEL can make measurements difficult. We did surveys across the ponds, measuring their depth and their width. And you may look at this and think, well, what's the difficulty? I mean, it really kind of looks like fun. And on that day, it probably was fun. Other days, not so much. The depths of these ponds can vary, and again, you want to make the measurements, but you also want to be very careful. So as I said, we did quite a bit of planning on this and had a good idea of what to expect. The teams on the ice just did a marvelous job of being persistent, adapting to things, showing ingenuity, and we really felt that we thought about everything. And we were almost right, because what we didn't think about was a global pandemic. This was an unforeseen challenge to all of us. And right before the rotation between legs 3 and 4, COVID hit. The aircraft that were supposed to do the rotation were no longer available. The international icebreakers that we arranged to do resupplies were no longer available. And there was a period of a few weeks where it looked like it wasn't clear if we were going to be able to continue. But through the persistence of the people that were on the ship, the people that were waiting to go on the ship, and the logistics team and the medical staff at the Alfred Wegener Institute, it was possible to come up again with a protocol where people would go to Bremerhaven, go into quarantine for 2 weeks, go out to the ship, and do the rotation that way. So we were able to continue MOSAIC with a couple data gaps and had no cases the MOSAIC. Now, early on in the planning, after we had our science question, the next question was, where do you want to go? Where should we go? And we decided, well, we wanted to start north of Russia, drift across in the neighborhood of the North Pole, and come out to Fram Strait, because that was an area where there's really a lack of good data. Now, once we decided where we wanted to go, the next question was, where do we want to start? Because getting this drift track was a little bit of a challenge. We were looking for a Goldilocks trajectory. We didn't want to go too fast and come out of the ice too early. We didn't want to go too slow and be stuck in the ice too long. We didn't want to go too far to the east and drift into the Russian economically exclusive zone where we would not be permitted to make measurements. And we didn't want to go too far west and wind up in the Beaufort Jar going around in circles for years. And so because of that, an extensive study was done looking at different starting places, taking data from satellites, tracking flows, taking model results, predicting where the flows would go. And this was actually the first scientific publication for MOSAIC. And it was decided that this was the place to start, and this was the most likely drift track. Now, so far, talking about MOSAIC, I've used a lot of superlatives. The biggest experiment ever, the most expensive, the largest number of people. But there's one superlative that I can't use, and that's first ever. Because we were far from the first ever. Basically, we were going in the drift track of Nansen. That's Fridtjof Nansen, the fabled Norwegian explorer, scientist, and diplomat and humanitarian, who had a similar idea. And his idea was to get to the North Pole by freezing into the ice and just drifting along. And he didn't have all these computer simulations or satellite data. His inspiration was somebody found some driftwood off the east coast of Greenland from a ship that was crushed north of Alaska, which made him think, well, maybe there's a general drift pattern, and if I can just get on that, I'll ride to the pole. And that was really an inspiration for us, and we often talked about how we were going in the drift track of Nansen. So how did that work out? Well, we can do this comparison. What you see in red is the drift track of the polar stern in MOSAIC, and in yellow is Nansen and the Fram. And there are some similarities. We both froze into the ice around the same date, Nansen the 22nd of September, MOSAIC the 4th of October, and we came out of the ice amazingly close together. Nansen came out on the 28th of July, we came out on the 30th of July. And the general drift track was pretty much the same across the central Arctic. MOSAIC actually got closer to the pole than the Fram did. So there are a lot of similarities, but there are also two differences. And one you can see just from this plot here, this map, and that's that MOSAIC started much further north. We had to. There wasn't any ice in 2019 where Nansen started. So we had to go further north to find an ice flow. The other major difference you can't quite see here, but even though we started around the same time and we ended around the same time, there was a difference. MOSAIC drifted out in 10 months. The Fram drifted out in 10 months plus 2 years. The drift of MOSAIC was much, much faster. And this naturally has gotten a lot of attention from the MOSAIC science team. From an ice perspective, the ice we had was a lot thinner than back in Nansen's days. And you would think that thinner ice, it's easier to move along. The atmosphere team is studying what the atmospheric circulation patterns and the winds were and trying to compare what we observed during MOSAIC to what Nansen experienced during the Fram. And even though the Fram's overall goal was to get to the North Pole, they did a lot of science. There's a 4-volume book of summarizing scientific results from the Fram. Now, there's an enormous amount of data that we're just starting to go through from MOSAIC. So there isn't time to even give an overall look at what's going on. So instead, I want to focus on one element of MOSAIC, and that's PROMIS. One of the things about MOSAIC was that each project had to have an acronym. And our project, here at THERE, we came up with PROMIS, Parameterizations for Optics, Mass, Ice, and Snow. The PROMIS team, we had 8 people from 4 different institutions. From THERE, there was Chris Polishensky, David Clement-Sewall, Ian Raphael, and me. From the National Center for Atmospheric Research, there's Marika Holland. From the University of Washington, Bonnie Light and Maddie Smith. And from the University of Alaska, Fairbanks, there was Melinda Webster. And the results I'm going to show are really the combined effort of all 8 of us. And I'm going to just take a minute to give a shout out to David and Ian. Ian left for MOSAIC in September of 2019, came home in March of 2020, spent a couple days, I guess, washing his clothes, went back to MOSAIC at the end of April, and came home finally at the end of August. David left for MOSAIC in January and came back in June. They both spent a huge amount of time up on MOSAIC and made incredible contributions, not just to our project, but the overall MOSAIC mission, because MOSAIC really was a combined collaborative effort. So what we were focused on in PROMIS, we had 3 main questions. And again, these questions were generated from a modeling perspective. Marika Holland at NCAR was our climate modeler, and she really provided a lot of guidance on what we should be looking at. First of all, there was albedo. How's the sunlight partition? How much is reflected, absorbed in the ice, or transmitted into the ocean? There's also mass balance. What are the processes that are affecting atmosphere, ice, ocean interactions, and how does that impact ice melt? And there was snow. What's the role of snow properties in controlling sea ice growth in the winter and sea ice melt on the surface in the summer? So these are our 3 main areas. Today, though, I'm just going to focus on albedo. But don't be disappointed, because I expect that sometime in the next year, you'll get to hear Ian talk a lot about mass balance and David talk about snow. So I'm just going to talk about albedo. And the reason I'm going to talk about albedo is, first of all, it's my favorite geophysical parameter for two reasons. One, it's simple. To measure the albedo, you get an instrument, point it up to the sky, take a reading, flip it over, take another reading, and divide. And you know ahead of time it's between 0 and 1. It doesn't get any simpler than that. Of course, it's not enough just to have a simple measurement. The second reason is albedo is important. It's a critical factor in any climate model. How much sunlight is reflected by the surface is of fundamental importance in climate models. And also, this is how sea ice becomes an amplifier of climate change, through the ice albedo feedback. You start off in the spring with this very pristine snow-covered ice that's reflecting around 85% of the sunlight. As melt happens, that surface gets darker, the albedo drops, and that means more sunlight's absorbed. As you absorb more sunlight, you get more melting, which lowers the albedo, which means you absorb more sunlight. And you get the idea. It's a positive feedback. It builds upon itself. It can amplify gentle nudges of the climate system into large shoves. And if you're doing a climate model, you have to get these feedbacks right. And that, with its role as an amplifier of climate change, we are very interested in the albedo. Now, the kind of measurements we made, albedo measurements we made, we wanted to look at the spatial and temporal variability of the albedo. We wanted to do that using spectral measurements and broadband measurements. For spectral measurements, we had an instrument where we could measure albedo from 350 nanometers to 2,500 nanometers. That's basically the ultraviolet to the visible to the near infrared. The broadband albedo was another instrument that integrates over the whole solar spectrum from 300 to 3,000 nanometers. So we were looking at spectral and broadband, spatial and temporal. And what we wanted to do is we wanted to capture these changes that we see. We start out in spring with this snow-covered ice that's really fairly simple. There's the snow-covered ice and there's the open ocean. And in the fall, you're back to snow-covered ice and the ocean that's starting to freeze. The summer is when it really gets complicated. You see this mixture of melting snow, bare ice, and melt ponds of all different colors and brightnesses. So it's simple in spring and fall and fairly complex in summer. Now, the other element of the albedo measurements was characterizing the surface. Now, it's easy to go out and measure albedos, and if that's all you'll do, you'll wind up with a whole bunch of numbers you'll have trouble making sense of. And that's why it's important to characterize the surface as well. We know that the albedo is strongly influenced by surface conditions, so when we were making these measurements, we also characterized the snow. How deep was the snow? Was it wet or dry? What were the grain size of snow? When the snow was gone, we characterized the surface of the ice. The ice often has a surface scattering layer of disaggregated ice crystals. We measured how thick that was and what the size of the crystals were. And then there are melt ponds. We measured how deep the ponds were, and just as importantly, we measured the property of the ice underneath the pond, because that's what really drives the albedo. And we worked with another team that were taking ice cores so we could look at the internal structure of the ice as well. And with this, and then we also took a picture of every surface we measured the albedo for. Because again, the solar spectrum has around 2/3 to 3/4 of the incident sunlight. So for albedos, to some extent, what you see is what you get. And with that information, we can interpret these albedo measurements. So let's take a look. It changes over space and time. And again, we made these measurements both for the spectral data and for broadband data. For simplicity, let's just take a look at the broadband data. And if you look at this, you can see what's plotted is the albedo on the vertical axis, distance along a 200-meter line in the horizontal axis. And we set out these 200-meter lines. You can see it in the image here. And the lines were set up to try to capture all the surface types that were on the flow, and to try to be representative of the flow. And the idea here was to get a sample that we could tie in to the grid cells in a climate model. And so we went along those lines, measuring the albedo every 5 meters along this 200-meter line. And that's what you see here. Albedos along the line for the different days during the summer from June 20th to July 29th. And from that, it's clear that there's a lot of variability. And that's pretty much the only thing that's clear. There's so much going on, it's hard to sort out what's happening. So let's break this down. And let's look at space, and then let's look at time. So here's the albedo transect for one day, July 27th. And again, you see these ups and downs. So let's zoom in and see what's driving those ups and downs. And you can see the lowest value with an albedo of around 0.2 is associated with a melt pond that's really dark. And it was really dark because the underlying ice was thin. We go along the line another 20 meters or so, and we see the largest value we've seen, and that's around 0.7. And that's associated with bare ice. Bare ice that has a surface gathering layer that's a few centimeters thick. It's deteriorated ice, but it looks like melting snow almost. And then going further along the line, we see an intermediate value of around 0.4. And that's another melt pond, but it's a much brighter melt pond because the ice beneath it is thicker. So here, again, we see that the albedo is governed mainly by surface conditions. And we can also now look at time. We can look at changes over time and just compare the first traverse during summer on June 20th, and the last one was made on July 29th. And you can see that wherever you look, the albedo has decreased from June 20th to July 29th as the melt seasons progressed. It can be anywhere from as little as 0.1 to as much as 0.3. You can also see that some of the features stayed the same. You can see some of the peaks and valleys, and that's melt ponds that formed and stayed there. Maybe they got a little bigger and they got a little darker. So we see that there's an overall decrease in albedo over time. Another thing we can do is we can go and say, well, okay, again, when we're trying to relate this to a large-scale model, what's the average along this whole line? You know, when we look at this mixture of bare ice and ponded ice, and we see that on June 20th, the average albedo along the line was 0.71. And by July 29th, it had decreased to 0.44. Now these albedos integrated over the line are important, and they're interesting because, again, it's a way we can start thinking about ways to incorporate results into models. So we did that for all the different days. We took the average along the 200-meter albedo line, and these are the results. Albedos up here, down here, the open circles represent the standard deviation of the albedo along that line. And if you look at this, you can see, three distinct areas. And the gaps are really due to the response to COVID. We no longer had icebreaker support. So that meant to resupply and to exchange crews, the polar stern had to leave the ice, do that outside the ice, and then go back in. So we do have these gaps in the data. But even with those gaps, you can see an early period in spring where the albedos are large, around 0.8, and that's because the ice is snow-covered and melting hasn't started yet. In this middle sequence, there's a general decrease with time. Again, that's during the melt season. The ponds are growing, they're getting bigger, the snow's all gone, and there's a decrease in albedo. And then finally, this increase in the fall, that's due to freeze up. The ponds are freezing over, the open ocean is starting to freeze over, and you get some snow. And you also see that there are these fluctuations. Now, turns out This wasn't the first time we did this kind of measurements. We did a similar sort of albedo line back during an early experiment called SHIBA. And SHIBA ran from October 1997 to October 1998. It was done in a completely different part of the Arctic, in the Beaufort Sea north of Alaska, and it was a completely different ice cover. It was multi-year ice, where MOSAIC was a mix of first-year ice and second-year ice. And what you see here is our evolution of the average albedo along those lines, along our 200-meter long albedo line. And when we looked at this, back when we analyzed the data, we decided that the albedo had 5 distinct phases in its evolution: dry snow, melting snow, pond formation, pond evolution, and fall freeze-up. Now, like MOSAIC, SHIBA was a measurement made at one place and at one time, so you're always a little bit cautious about extrapolating. But once you get over that caution, then you start saying, well, perhaps even though the nuances may be different, that you would expect there to be these 5 phases whenever you looked and wherever you looked. And we took it a step further by introducing the concept of the albedo accordion, that we have this time series, and it's really governed by when does melt start and when does melt end. And if the melt season's shorter, the accordion gets squashed. If the melt season's longer, the accordion gets stretched out. And if the melt season starts earlier, then the accordion gets shifted over. And so that was our hypotheses. And until MOSAIC, we never really had another data set to compare it to. But we can do that now. And what you see here is a comparison. The SHIBA results are in red, MOSAIC is in blue. And you can see there's actually pretty good agreement between the two. It's a different place, a different time, different ice, but we still see the same 5 phases. And interestingly enough, we have the same maximum albedo, which isn't really surprising because snow-covered ice, we had snow-covered ice in both cases. But we also wound up with the same minimum average albedo of around 0.4. So these two look like they agree pretty well. But again, it's an accordion. So we dug back through the old SHIBA data set and then the new MOSAIC data set and learned that the duration of the melt season was fairly similar in both cases, but SHIBA started 9 days earlier than MOSAIC. It was further south, so it's not really surprising. So what we did was we shifted the SHIBA data set 9 days later, and this is what we got. And this was really pretty exciting because you can see there's strong similarities between the two data sets. We get a nice match. And what that got us excited was the realization that maybe there are some generalities that we can use to improve the parameterization of albedo and climate models. Because that's the motivation, improving climate models. So that was the next step, to compare this to results from a climate model. And so what's shown here, again, it's albedo as a function of time. We see blue is MOSAIC with the dots, red with the dots is SHIBA, and then the blue line and the red line represent the average values from the Community Earth System model that was run at NCAR. And then kind of the broad shaded area is the range. They ran the NCAR model for 6 years at the location where MOSAIC was and where SHIBA was, and those bands give an idea of the interannual variability. And again, the agreement is pretty encouraging. The model albedo evolution has similar transitions. The broadband albedo agrees reasonably well, but there are some differences. First of all, the model is a lot smoother than the observations. And so we dug into that and we saw that what happens with the observations is there are weather events. You can be in the melt season when the albedo is decreasing, but it snows one day. And for the next few days, you have an increase until that snow melts. And similarly, in the fall, you can have snow-covered ice with an increasing albedo, and then it rains, and the albedo drops down. And that kind of activity isn't captured in the model. And one of the things we're going to do is to see whether or not we should be capturing it. Otherwise, though, there's pretty good agreement. And we were really happy about it until we started looking a little bit closer. And then we saw that in a model, two wrongs can make an agreement. In the community Earth system model, the albedo does agree reasonably well, but when you look closer, in the summer, the melt ponds really drive the albedo evolution. And so we can compare melt ponds from Sheba and MOSAIC, and then the curves are all the results for melt pond fraction from the model using the Sheba location and the MOSAIC location. And the bottom line is the model has a lot more melt ponds than we observed, almost twice as much melt ponds. And digging a little deeper, it turns out the model also has an albedo that's much higher for melt ponds. So you have these two things that kind of counterbalance. There's more ponds, but they're brighter, so you get decent agreement with the albedo. Well, that isn't what we want. We want to get the right answer for the right reason. And as we move forward, we're doing more work to use these observations to improve models. You know, currently, albedo is treated, well, CESM treats the sea ice with 5 thickness categories, from thin ice up to thick ice. And for each of those thickness categories, there's 3 surface types you can have. You have snow-covered ice, bare ice, or ponded ice. And there's 3 wavelength bands to get the spectral albedo and also the spectral incident radiation. And what we're working on is first increasing the number of wavelength bands to get higher resolution in the incident shortwave and on the albedo. And we're also looking at improving our understanding of the inherent optical properties of the ice. And we're reassessing the assumptions about surface conditions. You know, why are we getting so many melt ponds? And how can we adjust that to be more realistic? And we also want to assess the impact of weather events, the snow on melting ice or the rain on snow. And I say assess them. I mean, it may be something that needs to be included, or it may be something that is small compared to the other uncertainties. So we're working on several improvements to the treatment of albedo. And for MOSAIC, from the very beginning of MOSAIC, there was a realization that we all had our interests, things that we were concerned about, and papers to write and measurements to make. But the lasting legacy of MOSAIC would be the data. And from the very beginning, a strong emphasis was put on promoting data fairness and accessibility. In fact, everybody involved with MOSAIC had to sign a data set, a data agreement, saying that we would put our data set in an archive with complete data and all the metadata. We had a strong commitment to data sharing and archiving. Now, the field experiment's over, and I've had people say, well, MOSAIC is over, what are you going to do with the rest of your life? Well, the field experiment's over, but the fun is just beginning. There's so much data to analyze. There's still lots of outreach to do. There have been multiple special sessions at conferences. There are papers being published now. There's a special issue coming in the journal Elementa, and all the data will be available to anyone by the 1st of January 2023. There's a lot of work to be done with the analysis, integration, synthesis, and modeling of the MOSAIC data set. Now, of course, there's work beyond MOSAIC. In fact, just this week, another experiment has started. It's similar in many ways to MOSAIC. It's going to be a year or longer drift across the central Arctic. There'll be measurements made of the atmosphere, the ice in the ocean. And so in many ways, it's similar to MOSAIC, but there's one big difference, and that's there aren't any people. But what it is, there's an autonomous measurement platform that was deployed earlier this week that's really a mini MOSAIC. It has some but not all the MOSAIC measurements, It includes systems measuring properties of the atmosphere, properties of the ice, and properties of the ocean. And the data is transmitted back to us via Iridium sitting at home. It's part of a sustainable Arctic observing network because experiments like MOSAIC are big and they're expensive and they come along around every 20 years. But we want to have a more extended presence in the Arctic, and we can do that autonomously, where we can have stations out every year and have stations in multiple locations. The contribution from there to this autonomous network are ice mass balance buoys. It's a way to autonomously measure sea ice mass balance. We've deployed seasonal ice mass balance buoys that we get from a local company, Cryosphere Innovation, that is started and run by two Thayer grads, Cameron Plank and James Whitlock. And these buoys are based on the spar buoy design. In this new Arctic, a lot of the ice melts away every summer, so we want to have something that could at least function somewhat in the open ocean. So these spar buoys, they not only float, but they float upright, and they make a whole range of measurements, which you can see in this plot on the right-hand side. It's a time series from September through the following September. And there's a time series of barometric pressure. We can see when weather systems come through, of air temperature. Down on the bottom panel, you see that there's ocean temperature. We see the ocean right underneath the ice warming up in the summer. These red bars are estimates of the ocean heat flux, so we can see what's happening on the underside of the ice. But the really exciting part is in this panel here, where we can look at the mass balance. The gray area shows the snow building up through the winter and then melting away in the summer. We can see the amount of surface melting that's happening, ice growth in the winter, and ice melt in the summer. And the colorful contours are internal ice temperatures. And these ice mass balance buoys gives a way to attribute change. The satellites do a good job of saying, there used to be ice there, but there isn't anymore. These buoys can zoom in and say, because there's more melting on the bottom of the ice, or more melting on the surface. And again, we co-locate these with other instruments to extend the impact of the observations. And here's just a map of the buoys we put out in the past 2 years. It's the next best thing to being there. Now, I've been lucky, I've been able to study sea ice for a long time. And sea ice is just an incredible material. It's rich in its complexity. The scientific questions are fascinating. The engineering challenges are pretty great. But it's more than that. Studying sea ice now, it's not just an intellectual exercise, but there are consequences today. There are consequences for coastal villages that are having increased erosion due to autumn storms. There's also issues with the law of the sea, the question, who owns the Arctic? If you went back 40 years to the beginning of the satellite record, the answer would be, who cares? It's covered with ice. That's not the case anymore. As the ice retreats, there's increased emphasis on possible trans-Arctic shipping routes across the Northern Sea route. There's also natural resources on the continental shelves of the Arctic Ocean. There's also increased tourism. The ship there is the Russian nuclear-powered icebreaker, 50 Years of Victory. It makes 5 round trips every summer to the North Pole, taking 120 tourists on each trip. Down below it is a standard cruise liner, the Crystal Serenity, that a few years ago did the Northwest Passage. There's increasing tourism. And there's also the impact of this ice loss on ecosystems, which is something we're just really beginning to try to understand. And I expect there'll be a lot of good knowledge coming out of MOSAIC. And finally, there's an area of increased research, and that's whether or not what happens in the Arctic stays in the Arctic. Is there a connection between this loss of ice and mid-latitude weather? And so when we look at the Arctic, we have to, first of all, observe these changes that are occurring. And we need to understand those changes. And that's the only way we'll be able to develop a strategy to respond to those changes. Thank you for your attention.